Yeah, so we have quite a variety of experience as well as high level of experience. So actually more experience than myself. So it will be like maybe more of a discussion rather than like lecturing requirement in this particular course because of everyone's really high experience. So what I will be doing is to like from the feedback that I get, so there's no point of me to like go into very high detail, like very in-depth details of the material. So anyway, this course itself is a self-paced course as I have been instructed. So I will upload the material, and what we will do is like we will basically do it on a self-paced manner where I will upload the lecture material depending on the feedback that I got. So I formulate based on as I explained earlier, on the content that is provided over here. Let me share that once again. So this is the content that I have been received, and in this particular course outline and the content, we are to look at the operation and maintenance requirements of cogen, combined cycle and integrated gasification combined cycle power plants with gas turbine applications in power stations, protective systems and tests, steam turbines for combined cycle power systems, and integrated gasification combined cycle power plants, the process, and then from the thermal to hydropower generation and maintenance. Uh, and in that one, basically to look at the equipment itself before going into types of maintenance and operation and maintenance of solar photovoltaics, PV plants, and their operate maintenance strategies, and general guidelines of power plant operation and maintenance, taking over plant for O&M, manpower selection and training, and different aspects. So actually, I have started my material going in with the hydropower operation and maintenance. Mainly the material that I have uploaded is regarding the plant equipment and operation. So what I will be doing is I will upload uh, a recorded lecture as well as the slides and the material that is necessary for each of the components. And why after going through them individually, like we will meet at the next meeting time, and then we will have a discussion, because that will be beneficial since from the feedback that I got from all the participants, there's no point of me like wasting like your time as well to explain everything individually. So I will give you like, so we will meet once every week, and then during that week I will upload the material uh, with the slides as well as the recorded lecture, where you can see, and then you can point it out any things that you want to discuss. And it is necessary that like since the combined experience of the all the participants is like much higher than myself itself, it is better that you can participate in the discussion of all the others questions, like everyone is like basically learning together. So that will be much benefit. So can you hear about your feedback on that? What do you think about it, or do you need a different approach?
Yes, I think that's going to be helpful to everyone.
Yeah. Okay. Any other suggestions or comments on the delivery?
Yes, I also think that because we are having a lot of people in different industries, I think everyone can contribute, and then everyone can learn together.
Yeah.
I
Okay.
think that will
That
be best.
sounds good. However, I think since what's practiced here in Sri Lanka is not really always up to the standard, it would be beneficial for a lot of us if the global context could also be related, other than
Okay.
just our experiences as well.
Yeah. Anyway, like most of the
Because
examples
as per
that
what I have been seeing so far, what we do here in Sri Lanka is not really always right. We do have different changes when it comes to the peripheral services within the plans, and also at times it's really questionable whether the OEM approvals and recommendations are being prudently or strictly complied here in Sri Lanka. So I thought if we can also incorporate the global and the theoretical concept as well, that will be beneficial for all of us, sir.
Okay, yeah, thank you very much for that. Yeah, that's a good comment. Yeah. So I'll take into account on that feedback. So yeah, okay, that actually I haven't thought about that much. So yeah, that I can be ready for the next meeting with you. Okay, so any comments further? No. So for the time being, so I have arranged this. That's my no, not that one. Let me just say, let's see. Give me a second to, yeah. Yeah, so to start with, I have been working on with the hydropower operation and maintenance. So in this case, what I will be mainly concentrated about is the what we are mainly looking at is first sorry, this is the wrong set of slides. To basically look at the the equipment, hydropower plant equipment and the operation as a starting point. And we will move on to the other sections as we go on. So this particular lecture note that I have already uploaded into the fields, I think you have access to the fields site because I can see you as participants. There are 29 members. Students registered in the course. So there are 29. So I think you have access to it. So I will upload the material here, both the lecture PowerPoint or the PDF file, as well as the recorded lecture material, which I would include over here. So for the time being for today's discussion, we will talk about this hydropower operation and maintenance to start with, with their hydropower plant equipment and their operation. So as you may know, hydropower is one of the key generating schemes that we have in our generation mix, and it plays a crucial role when we want to basically have a dispatchable generating source. So these are some of the photos that I have for hydro generation schemes in Sri Lanka as well as globally. So you can see most of the main thing associated with the hydropower is hydro or water. So there's a main scheme of basically managing this water resource and using it appropriately to generate power is the key aspect of the hydro generation. The other main concern that is associated with this is that the level of investment which is required for this generation. So we need really large dams to constrain the flow of water to make a reservoir, and then infrastructure to bring that water into a power station via different hydraulic channels. and then use that water to drive a turbine to generate electric power via a AC generator. So the schemes, depending on the megawatt size as well as the generation size, the size of the scheme varies dramatically. So compared to the global scale on the photos that I have on the bottom of the slide, the scale of Sri Lankan generation is quite small that you can see. So as explained by one of the participants, the global aspect is not covered in most of our operation and maintenance strategies that is used in in our country. So that bypass has been mainly, in my opinion, has been due to the level of scale of this equipment. So in a power station that is quite dependent on the size or the major like depending on the investment as well as the amount of damage that the dam itself or the power station can impose, creates a larger risk into the particular country or the area. So based on that indicative only, I think there has been some like what do you call, and not that much what do you call, the prominence into the operation and maintenance strategies used in the power plants. So here are some of the key few examples of damages or disasters that happen due to poor O&M practices. So you can find about them, and I have actually included a few videos from YouTube regarding two of those damages. So one is the Oroville Dam spillway damage, spillway breakout, what happens there. And so there are two videos actually included. One of them is regarding the damage itself, what happened during the problem, and the other one is on the recovery process and how they restored the project, how restored the dam and the spillway after the disaster happened. Then I also included the video, so coming from the same channel, the practical engineering on the Taum Sauk pumped hydro storage dam. So all these three videos, so basically whatever the material that I need to cover on the hydropower generation, operation and maintenance is practically covered in these three videos. So it is highly required due to
long-lasting fragrance, unshakable.
yeah, to go through those videos. I have included the PowerPoint itself, so you can directly access those videos through the links and have an look at those that explanations as well as the problems to get a better overview. So any comments? Any yeah, so this is in the chat. Okay, no. Yeah. Any material that comment that you have to provide me at this stage? Yeah. So yeah. So to start with, we will go with the basics. So before going into the maintenance, we need to first look at what happens, what is basically required, what is the components and what do we have in a hydropower station. Mainly, as we explained before, we have a water source, maybe primarily it's a river flowing in, and we create a dam to make a water reservoir, and the output of this water reservoir is taken from a tunnel via an water intake into the tunnel, and that tunnel usually flows in a horizontal manner, and in order to generate power we need to have some kind of a head. That means the water height difference between the turbine and the water reservoir level. So that head difference is achieved via a penstock. So penstock is a metal tube, basically that can withstand high pressures, and the tunnel is a could be a concrete reinforced tunnel or a tunnel going through the natural stone on the geographic arena. Because the tunnel is a horizontal structure, it doesn't have a higher pressure, and it's normally a low pressure channel of hydro conduction, and the penstock is the element that withstand the high pressure of the water. So in the region where we have the interconnection between the high pressure and the low pressure regions of the tunnel and the penstock, we have a surge tank, which is an well extending above the surface to basically act as a shock absorber to any pressure differences coming within the penstock to avoid them to move into the tunnel. So any high pressure waves that can appear in the penstock, if they are left to move into the tunnel, that process can basically create the high pressure spots in the tunnel that can damage the tunnel outings and create provide damages into the final circuit to the tunnel infrastructure. So once the water comes from the penstock into the power station, it is being directed into a turbine. So the turbine arrangement is different. So we will look that in later when we go into the different categories of turbines. And this turbine is connected to a generator via a driving shaft, turbine shaft, and the generator spins due to the rotation of the turbine, and electric power is generated in the generator. And after the switch yard, which is outside, it's not indicated here, it will transmit the power into the transmission network. So the water coming from the turbine will go into the tail race and exit the power station into the outflow, through the outflow into the downflowing river, and the water pathway will continue. So naturally, in hydropower generation, as a good practice as well as an environmental concern, it is required in most of the cases to put the outflow into the same river where the water has been extracted. But there are some schemes, even in Sri Lanka, that this is not followed. For example, the Ukkuwala power station, the intake for Ukkuwala power station is at Polgolla from the Mahaveli river, and that it is returned back into the different river. I can't exactly remember this Kaluganga, Ambanganga, I'm exactly not sure. Ambang River in Matale district, which is a little bit far away from it is not the natural river that it has been transmitted. So the water will eventually end up in Mahavali River, but it is not the exact crossing that happens. So I think the same question was roused with the Umaoya projects, but there are some concerns with regards to the water from one river being diverted into another river via a hydropower station. So that's just an environmental concern that I wanted to highlight. But yeah, so any questions, concerns? Maybe some, the actual facts I might have to check, but those are some concerns that I have that are rising in the hydropower industry. So no comments or anything on the chat or voice, so we'll continue. So when we talk about hydropower O&M, so hydropower converts potential and kinetic energy of water into electrical energy, and efficient operation and maintenance ensures reliability, longevity, and safety of this power plant. And there are mainly few sections in the as I explained in the hydropower scheme: water intake and conveyance, turbine and auxiliaries, generator and auxiliaries, transformer and the switchyard, and other supporting systems like the lubrication, cooling, control, and drainage systems in the hydropower station. So with these O&M practices, we ensure continuous, safe, and efficient operation of the power plant, minimize force outages and losses, maintain equipment and optimal conditions to design life. So this is important because hydropower stations, they require major construction, major investment, and also results in major changes to the environmental aspects. So when we create a hydropower station, we create it for the long run. So typically to about 50 to 100 years, at least of operational capacity is required from these power stations. So this concern has been the construction of dams for hydropower has been a major concern in United States, where they are actually retiring some of the hydropower dams to make sure that different species of fish and the natural habitats of in the rivers uh, return back into the pre-existing conditions. So the design and construction of these hydropower stations has been the result of different conflicts, like conflicts of communities as well. So making a hydropower plant is not a major renewable concern in the point of view of the modern society. So few years back, like in 1950s, 60s, in the 1900s, basically hydropower was the way to go because it doesn't create almost zero emissions. Powered from water, if it rains, you have the hydropower. But with the growing concern regarding the how, good practices regarding communities, conflict avoiding in communities, hydropower has become a generation source which has a lot of questions. So as I said, the North American, like the indigenous community, the power plants created in indigenous communities has created some problems with regards to relocation as well as the disruption to the environment. There has been some problems in New Zealand as well. The Manapuri Power Station hydropower generation scheme, which is the largest hydropower scheme in the southern hemisphere for quite a bit of time. It's about 800 megawatt power plant. So the power plant itself, the hydro scheme disrupted quite a large space associated with the Maori landscape. So there were some conflicting construction of hydro schemes in all throughout the world. So so it is quite important on the what is the correct practice as well as the correct maintenance, the optimum maintenance of these assets because they have been created with different conflicts, and it is bit ideal to maintain them without causing much further damage in the downstream like throughout the time. So yeah, so that's under the come to protect environment and downstream communities and uphold professional ethics and safety with regards to this area. So then to start with, we will go through the different components that we have associated with them. The hydropower scheme. So we'll have a simple look at it. Uh, all the components to get an idea so that everyone is in the same picture. So we know what we are talking about. Then we can go into more details of regarding the operational and maintenance strategies and what are the different aspects that we want to discuss with them. So in this scheme, so we have the water intake and the conduit system. So the main purpose is to direct the water from the reservoir or rivers into the turbine, and it controls the flow, prevent debris, and maintain stability in the in this this structure and water flow. So it comprises of an intake structure with the gas and trash tracks and inlet channel and tunnels and gateways and stop locks. So here we have the intake, the photos of the intake. So you have the intake structure. So on the left top, you can see that structure. So the tunnel intake, it has this gate hoist as well as this intake structure, which has the trash screen. So I have a separate photo for that. So this trash screen is just a grate covering the intake so that the debris like logs and other elements don't go into the water intake tunnel and damage the our intake or the tunnel structure, penstock structures associated with the hydro generation scheme. And we have the gate hoist. So basically, when you want to block the intake, you can use the gates that in the intake to stop the water going into the tunnel intake. And we can do maintenance on the tunnel. So I have also included a photo of the tunnel of the Umaoya tunnel with the TBM machine or tunnel boring machine at the intake in the take. So you can see it is under so this is the region where it is being filled with water. So it's still under the construction. So you can see how the tunnel intakes looks like at the construction stage. Because there it is like a very limited chance that you get to see an intake of a tunnel when it is in the dry state, because you can't almost after putting like after having the water in the reservoir, you're never going to able to see this view of this tunnel intake for a particular power station. Then you have these stop logs as well. So these stop logs, they can are also used to like stop the flow into the water. So they run on these rails that extend into the water. And when you want to stop the water intake, like intake into the tunnel, you can place them at the tunnel. You can bring them down and stop the water coming into the tunnel. So the amount of maintenance work that you do in a tunnel in a hydropower scheme is quite minimum. So there have been only about few recorded, I think, recorded maintenance done in Sri Lanka under in hydro tunnels. So I have a personal experience in a tunnel maintenance done in New Lakshapana. Is it New Lakshapana or Lakshapana? Yeah, one of the Lakshapana tunnels where they had to stop the water intake and basically dewater the tunnel and like a plug leak that has been happening for quite amount of time. So the dewatering a tunnel is a major challenge because after the tunnel being underwater for quite a bit of time, like that tunnel was dewatered after about 30 or about 40 years of operation. So the inner structure of the tunnel is being withstand by the water pressure on the tunnel. So when you dewater a tunnel, all that water gets removed and the structure, the stone and the other structures in the tunnel itself might get damaged due to the loss of pressure in the tunnel. So it's a very delicate process as well as doing maintenance work or repair work in a dewatered tunnel is quite challenging. So that's some quite engineering expensive maintenance work that carries out in those tunnels. So therefore, it is to avoid damaging to the tunnels. The first practice is to build them correctly. So build the tunnel in parts where we have good cover, like good geological conditions, as well as maintain the intakes with good trash screens and other stop logs to avoid damages, avoid any debris going into the reservoir, into the intake, which can result in damages in the longer run. So this is some of the same example explanations. So the trash tracks prevent debris entry, clean manually or mechanically. So quite trivial. Intake gates, they isolate the penstock for maintenance, operated hydraulically or electrically. Yeah, so these operational characteristics, so based on the whether they are hydraulically or electrically, their maintenance characteristics can be differ. So maintaining an hydraulic system has its own challenge compared to an electrical system. So yeah, in the stop logs to temporary closure for dewatering during maintenance, and gate hoist lifting mechanisms require periodic testing and lubrication. So the thing is that even so, as we see here in the intake, we have mechanisms to do temporary closure for dewatering and isolating the penstocks and this kind of arrangement. So as I explained previously, these kind of maintenance happens quite, they don't happen that much regularly that we want to dewater the tunnel. So that means these assets in the intake are not that used, or they might be just there waiting for the maintenance that is coming after about 10 or 15 years. So at that particular moment, we have to make sure that these elements work as well as they are maintained throughout the time. So for example, if we say that we are not going to get a maintenance work in the tunnel for about 30 years, so we can just forget about the trash screens, gate hoists and the trash racks and things like that, and the stop logs. So we can wait and we say that we will do any maintenance at the time we want to do this tunnel dewatering. So by that time, these intakes and these stop logs might be at the condition that are very like degraded, that they cannot be even repaired. So at that condition, at that state, you will not have a resource that can basically temporarily close the water into the tunnel. So then you will have to basically create a dewatered area, like building a dam across the resource intake, across the tunnel intake, and it will be a really expensive job to carry out. So basically, maintaining these elements in the water intake that are not that used needs to be properly tested and maintained for proper operation of the power station. So as I explained here, like in the O&M of water intake, so we need routine inspection for corrosion, blockage, and vibration. As we said, like corrosion is a major factor because the intake is submerged in water. So we make this intake with metal, with steel for the strength, and it is very likely that they can corrode. So frequent painting, and making anti-corrosive action is important in this kind of structure. Then we need to do cleaning of trash racks to prevent head losses. So you can see in most of the intakes in rivers, particularly in Sri Lanka, the water intakes to hydro schemes looks like something like this. So even without human-made what do you call, like waste and pollutants, the pollution like the debris coming from forests and like trees can also accumulate and cause severe intake damage. So we can see, like after the huge rain, like in Kandy area, like the Polgolla Dam, the intake for the Ukuela power station gets almost blocked from the pollutants coming in from the Mahavali River. So proper cleaning them and avoiding jamming on this trash rack as well as the gate is necessary for proper operation. And so ensure safe working operating procedures when personnel enter intake channels. So most of the cases, when you want to clear out these intake channels, people have to go into the intake channel to clear out these intakes. Most of the they are carried out by divers working in near invisible conditions because the water is quite muddy and the water is not transparent in most of the hydropower schemes. The water is not clear, so the divers has to go almost blind to clean out these water intakes, and it's a really expensive job irrespective of the country that it is being carried out. So it's a very extremely dangerous job and very high health and safety concerns. Uh, Apart from the physical damages, there are concerns regarding infections as well. So you need to have proper mechanism as well as routine maintenance to avoid those kind of actions. Then we go down the tunnel to water conduit system. So this includes the headrace tunnel or the channel. So most of the channels are used quite minimum in Sri Lankan context. Mainly they are used in mini hydropower schemes. Major power schemes, they mainly use tunnels, but the channels are used to conduct water from the reservoir to the generation scheme in most of the many countries. So I know some examples in New Zealand, like the Oahu power generation scheme in South Island of New Zealand. They use these channels to carry water from the reservoir towards the generator plant. Then you have the surge tanks, penstocks, and valves associated with them. So we'll see what they are doing separately. So their main job is to this conduit system is to transport the water efficiently with minimum hydraulic losses. And regarding the O&M activities, inspecting lining, joints, and expansion anchors on the penstocks, and monitor leaks, cracks, and sediment accumulation in the tunnels, and test pressure relief valves and surge control devices associated with the conduit system. So here are some of the some photos of these elements that I am talking. So you have the headrace tunnel. So this is a horseshoe type tunnel. You can see with the characteristic design or the cross section of the tunnel. Then it is a low pressure. So you can see there is no head change. So it is a horizontal tunnel. So you can see the head, or it has a very minimum pitch into the tunnel, like very low slope to avoid any, it has a very minimum slope. And here I have included a schematic diagram from the Umaoya dam structure or the tunnel structure, tunnel layout. So you can see there are two dams in the Umaoya scheme, Puhulpola Dam and the Dabara Dam, and the two dams are interconnected with a linking tunnel. And the main headrace tunnel, it has a very low inclination. You can see the length is 15.2 kilometers and only the drop is 4.3 meters throughout the whole 15.2 kilometers. Even the linking tunnel, it's a 3.9 kilometer long tunnel with a 4.5 meter drop. So it's a very small slope in those two tunnels to avoid hydraulic damage into the tunnel. And then at the pressure shaft or the into the tunnel, so you can see it's very high drop, almost 90 meter. So here the other aspects are the surge shaft. So the one that I said to basically eliminate the surges appearing from the pressure tank. into the pressure tube shaft or the penstock into the tunnel. So it looks something like this. And the penstock, they are metal tubes, pipes, basically carrying out the high pressure water down very steep slopes. So the other aspect is that in the placement of the surge tank, if we can't directly place it at the end of the pressure shaft, the tunnel part should be realigned. This section should be realigned with metal strip, metal tubing, or penstock itself to basically provide the necessary high pressure operational aspect or the capability for the tunnel. Then we have the main inlet valve, or commonly known as MIV. It is the main valve that is stopping the water into the generator, but it is not operation. It cannot be operational when the water is flowing. So this is a valve that is operational when we have stagnant water, and if we require the MIV to operate at when the water is flowing, it is like a one time job. That means after, if you are to do that task, then due to the immense pressure of the water, most probably the MIV will be out of service. Like you have to be replace the MIV after that operation. So it's a really, because the water pressure is really high, and therefore the MIV is operational only when we want to do some maintenance in the generator. When the water is stopped, then stopped at the generator locally, we can stop the MIV. So you can see there are channels of to water to basically balance the pressure on the both sides before opening or closing the MIV. So it is to basically withstand the immense pressure of the penstock intake. So the water coming in, the high pressure head gets stopped from this main valve at the end. So with regards to the maintenance of each of these items, for surge tank, it absorbs the water hammer and pressure fluctuations, and regular inspections. Therefore, we need to do regular inspections for air vent blockages, cracks, and corrosion. So since this is a well, like a normal water well that you have at your houses, you can get different debris, trees getting enlodged in the cracks, and they are getting growing on those cracks, and corrosion of metal parts, they can happen. And actually you can there's a video of in this link, you can go into this Reddit link. There's a video of a surge shaft being operational, where you can see the large surge coming in through the penstock being dissipated in the surge shaft, and that amount of pressure relief can be can cause cracks and different blockages in the surge tank itself. So it is necessary to regularly visit this and basically conduct the required checking on them. And then regarding the penstock, you have the steel or concrete conduit high pressure under high pressure. So this one. So you need to inspect the wells, supports, and anchor bolts, blocks like this, and then apply anti-corrosion coatings periodically, because this is a metal or the steel pipe carrying water. So you have to do that periodically. So you wash you have to remove the rust from the inside as well as from the outside, and apply paint inside as well as outside. So you can see a corroded penstock over here. So you have to do maybe sandblasting within the pipe in the penstock itself, and monitor for do painting inside the pipe. So to basically do this job, it's also a really expensive as well as dangerous job, where you have to climb up the pipe in the dark with lights and very enclosed space, crawl through the pipe and basically do the cleaning as well as painting of this pipe. So that's on the water conduit system. Any questions? Yeah. Been disabled. Okay. So we will continue. So we will continue for like we have, yeah. So we'll do this part, and then from the next section onward, we'll do recorded lectures material, and then we will have the discussion. So regarding the turbine and so we had the water coming from the conduit system, and now we are at the turbine level. So there are the turbine's main purpose is to convert the hydraulic energy into mechanical energy, and there are mainly 3 types of turbines. So doing most, because most of the people are from mechanical background, you might be more familiar than on these turbines than me. So the Pelton turbine, Francis and Kaplan. So Pelton turbine is this one, which is the impulse turbine, and a Francis turbine is a reaction type turbine, and a Kaplan, it's kind of a propeller turbine. So in Sri Lanka, we have the Pelton turbine in Lakshapana Power Station. Both the new Lakshapana and old Lakshapana has Pelton, and almost all the other generators have Francis turbines with spiral casing. So the selection of these turbines depend on the head and the discharge. So it is a design decision that takes to identify what is the turbine that you are going to use. And so with this turbine, there are major auxiliary systems. Governor system, which mainly controls the amount of water that is hitting the turbine. Lubrication and cooling systems, because the turbine is a mechanical device mounted with the bearing, and the bearing, the connection point should be having good lubrication and cooling, and hydraulic pressure units or HPUs for other control actions. The flow control, the water to the turbine is being directed via wicket gates or the nozzles. So nozzles are being used in the Pelton turbine structure, and in the other Kaplan and the Francis turbines, we use wicket gates that are the wicket gates. What they do is the water that is coming from the penstock is fed into the spiral casing, and from the spiral casing, the water into the turbine is being directed through the wicket gates, through these small gates that are enclosing the spiral casing. And depending on the water that is required for the turbine, the angle of these wicket gates can be controlled externally, and they can be going from the stop position to the fully open position by controlling the angle of these wicket gates. So basically, the water flow, when the valve that is controlling the water intake when it is flowing, or when the water is not stationary, are the wicket gates or the nozzles, not the main inlet valve, as I explained earlier. So the wicket gates and nozzles, they are very dynamic devices, and they needs to be properly maintained because they withstand the high pressure as well as they operate in dynamic state. And the operation of these wicket gates and the nozzles are maintained by the governor, and looking at the frequency as well as the primary frequency response that is governed by the electrical operation of the generator, controls the amount of torque applied to the generator, and the torque is changed by determining or changing the amount of water passing into the turbine. And the governor will link because the speed of the machine is dependent on the frequency of the grid, power grid. So as we explained in the electrical aspect, in the hydro generation we use synchronous generators. We can, because almost everyone is familiar with the aspect from the participants profile, it seems that you are familiar with that concepts. The generator is operating as a almost constant speed, which is synchronized with the frequency of the power grid. And when you increase the water that is impacting the turbine, it is only increasing the torque or changing the torque, and the governor's job is to do that, changing the torque. The turbine's efficiency depends on the head stability and guide vane setting, and draft tube pressure, and the cavitation control and sediment handling. So head stability means like if the water head fluctuates dynamically, or that means the water that could happen, like any water losses in the penstock or leaks in the tunnel. So those kind of elements could cause head instability, and guide vanes, that are the wicket gates that are covering the spiral casing. So based on their settings, the efficiency of the turbine can depend, as well as the cavitation and sediment handling on the turbine could cause the efficiency reduction in turbines as well. So this figure shows the cavitation effects on a Francis turbine and a Kaplan turbine. So you can see the small water droplets, air bubbles that are appearing on the turbine blade can cause this cavitation. Basically, very high speed air bubbles cause like a sandblast effect on the turbine and cause these rough patches. So this is a severely cavitated turbine which is almost deteriorated. And to avoid this, you need to do daily checks like vibration, oil pressure, and cooling water flow of the turbine. So if you see any increase on these parameters, that means we are having some issues with the turbine operation, and could probably result caused by some of the damages that we explained here. And periodically, the power plant maintenance should look at the runner and the blade wear, seal inspections, and alignment to see how they are performing. And so to do that, so like it's not that much of a time consuming work. So for the hydro turbine, this can be done relatively easily with a small opening inspection. You can do these inspections, and there are inspections that you need to shut down the power plant, like overhaul bearings, inspecting guide vanes, and remove sediments. So those things you need to basically shut down the power plant and go inside the spiral cage and do these changes or inspections. So the planning of these checks should be done accordingly to have the best efficiency associated with them. Regarding the safety and environmental aspects, so maintaining safe hydraulic conditions to avoid surges in the water hammer, and isolate turbine during maintenance to ensure gate closure and dewatering, and minimize oil leakage to tail race. So using biodegradable oils where possible, because that's a major concern with the hydro turbine generators, the oil leaks that can happen, because many synthetic oils are used in the generator bearings, lubrications, as well as in the transformers that we explain later. So they are very dangerous carcinogenic material. So proper use of them or using biodegradable safe oils or lubricants wherever it is possible are a must in those operational settings. So that's up to we came up to the turbine. So now where the electricity is being generated is the generator. So there are two main types of generator arrangements, the horizontal axis and the vertical axis generators. Horizontal axis, we have them in Sri Lanka in Old Lakshapana Power Station, and vertical axis generators are the most popular power plant generating plants units in hydro schemes throughout the world. So horizontal axis are used in small scale mini hydropower stations as well. But large scale horizontal axis turbines are, to my knowledge, are in Old Lakshapana Power Station in Sri Lanka. That's the only usage. I might be the knowledge might be incomplete there, so yeah, I need to find that out. It's not an essential thing. So we will look at the main parts of the hydro generator coming with the turbine. So in this case, we have a Kaplan turbine where from the water from the spiral caging, the water is inside the spiral cage, and using the Wickert gates, depending on the Wickert gate angle, the water gets inserted into the into the turbine, and the turbine rotates. And the turbine and the generator shafts are coupled at the middle, and then at the top you have the generator. So always the generator is at the top because the water has to go from the bottom to the tailways towards the outflow of the power station. So generator is located at the top, and due to the movement of this turbine at the same speed, the generator is rotated. There are no gearbox between the two shafts. The generator comprises two main windings. One is on the rotor and the other winding is at the stator. So this is, since most of you are from electrical engineering background, this is quite trivial, or you already know this. And we basically take the electric grid is connected to the stator via a generator transformer, and the rotor is excited through DC power to produce a magnetic field on the rotor windings, constant magnetic field. So with regards to the control systems of a generator, this indicates how in a simple manner, how the working fluid or water is being directed to the turbine via the governor system. So you have the working fluid. So this is in general true for both thermal as well as hydro generators. You have the working fluid, the water in our hydro case, coming in from the I'll say this example for our hydro case to make it more clearer. Yeah. So this is the hydro. So up to here, you have the main inlet valve coming in with the water. So in this one, we have actually an incorrect word here, the main inlet valve. It is not correct. It will be the Wickert gates. So the nozzle for our hydro scheme. So these Wickert gates and the nozzle, they are, as I explained, they are controllable valves, so which can operate dynamically. So what happens in the governor, where we in the control aspect of this working fluid towards this turbine, is that through the governor system, we control the operation of these wicket gates or the nozzle. So what we do is we in the governor we have a governor mechanism, something like this. So this is a mechanical governor which you might be familiar because you're coming from a mechanical background. The governor is being spun at, is driven by the turbine shaft. So the turbine shaft, it gets this measurement through a mechanical path or an electrical path, because the governors now, almost all the governors are electrical. There are mechanical governors in hydro stations, but very limited. But it is easy to explain through this mechanical governor the process of the governor control. So the speed is taken and it is driving the governor unit, the mechanical governor. And when it is rotating, you have these metal balls from the mechanical governor. So depending on the speed, the balls move outside or inside into the on this rotational axis. So they are rotational on this axis. So when they are rotating with the operational speed, if the speed is high, the governor will move out. These metal balls will move out, and due to that movement, this particular sleeve will move up. So moving up indicates movement of this pilot valve. So it will be basically moving this up or down. So it will cause a movement of this particular pilot valve on one direction. And in this pilot valve, it is a cylinder which has two intakes of high pressure oil. High pressure oil. So this is maintained with an oil reservoir and an oil pump. Oil at constant pressure, so that is maintained. So with this, you will move this plunger of this pilot valve up or down, and based on that plunger position, the oil will flow through the top path. So oil will flow through here, or oil can flow through here depending on the plunger position. So in the position that we have on this figure, the oil will move like this, and it will fill up this part of the hydraulic servo motor. So this is a large piston. It will fill out this chamber, and it is going to reduce the material that we have over here. So that will cause the hydraulic servo motor to move down and then cause some movement in our wicket gates and nozzle. So similarly, when the speed reduces, the balls come into the middle, and that will cause the pilot valve to move in the other direction. And since the pilot valve maintains the high pressure oil, it will drive the hydraulic servo motor in the other direction, creating a displacement in the opposite direction. So basically, in that action, the governor controls these wicket gates and the nozzle to maintain dynamically control working fluid into the our generating scheme. So it converts, the governor is a generator converts mechanical to electrical energy, and synchronous generators used stator stationary winding, and the rotor is the field winding or the rotating winding. Operators constant speed determined by turbine type and grid frequency, and power system. So power system operated with generation and load balance. Any change to this balance is replicated as a frequency change. So that's the main principle of the power system generation, that the generation and the load should be balanced. And when we have any differences between the generation and the load, that is replicated as a change in the frequency. So a change in the frequency result in speed variation. So that's the action in the governor as well. So when the electrical system has less power required and the turbine is the mechanical power from the turbine is remaining constant. The generator is it results in the generator to overspeed, and that overspeed is detected by the governor, and the governor takes necessary actions to move the pilot valve, which in turn takes action to change the hydraulic servo motor, which controls the wicket gates of the nozzle to reduce the power output or the mechanical power output going into the turbine. So this action is typically with regards to the electrical dynamics on the power system operation. The governor is relatively slower compared to the electrical dynamics, like the faults or load changes that happen. So there are different dynamic time frames or time constants associated with the electrical power generation on hydraulic generation schemes. So it is necessary to properly identify them. So the other control system associated with the hydro generators or synchronous generators in general. So this is true for the thermal generators as well. Both of these control systems. The other one is the excitation system. So as I explained, our rotor circuit is a magnetic field, is a constant magnetic field. It is produced by a DC current. So the main job of this excitation system is to provide a DC power supply into the rotor conductors, rotor winding. So what it does is it has a what we do is we have there are some brushed exciters as well as brushless exciters. I haven't included the figure of this system actually, which I couldn't include. So what happens is that this particular winding is our rotor winding. So this is the rotor winding. And when we look at the cross section of so I have a horizontal generator. So this is my rotor generator shaft. So this is my magnetic winding of the rotor, which has the winding, and that winding is being connected connected into slip rings of the two poles. So these are slip rings. They are individually isolated metal rings connected on the shaft, and to provide DC power, we have brushes like the normal DC motors that you have learned in your ordinary level classes. You have these brushes touching them, which we provide with the DC current voltage source. So this DC voltage source is the problem that we encounter, because we can, by having controllable DC voltage and DC current flowing into this rotor magnetic field, we can control dynamics of the generator in the electrical aspects. So the job is to basically, from this excitation system, is to provide a controllable or a variable DC source. And you can't, the other characteristic is that this particular winding for larger generators draw about several thousands of amperes into the winding. So having a suitable power converter or a DC voltage source that has this capability to provide variable voltage to a moving winding is the problematic system of this excitation system. So this is the most basic and the older type of excitation system where it uses brushes to do this. And the variable part is being created using this thyristor circuit power rectifier, which is since we use thyristors, we can achieve variable voltage on the DC link, or variable DC voltage by controlling the operation of these thyristors. and the variable power is being provided into the via a crowbar. So to basically protect the rectifier and the excitation circuit in the event of a fault via the brushes to our rotor winding. So there are other developments, and most of the current synchronous generators are using brushless excitation systems that has a rotating rectifier mounted on the shaft itself, which is being powered by a pilot generator connected onto the rotating shaft. So you can read on them, because this one has this particular excitation system has a main maintenance limitation, because we use the brushes and the slip ring arrangement. So because of this arrangement, we need to frequently do maintenance on the brushes and the slip rings. Replace brushes. We have to look at the generator enclosure for carbon dust due to damage to the brushes. So that needs to be properly looked after. So with that, the control of this power rectifier. So this part, the whole thing, we call it as the exciter with all the auxiliary circuits. So the power rectifier gets power through another excitation transformer, a three-phase transformer, which is powered by the generator itself. So this part we call it as the exciter. And how this controllable rectifier operates is dependent on the AVR, or the automatic voltage. So it is in simple form, it is just a PI controller looking at the generator terminal voltage and maintaining the voltage based on the power provided to the power rectifier on the excitation circuit. So because in a synchronous generator, the output terminal voltage depends on the amount of excitation that you have on the rotor winding. So I'm not going to go into much of the theory on the synchronous generators. Basically, the output terminal voltage magnitude can be controlled by the amount of current passing through this rotor winding. So in order to control the amount of current, the AVR controls this controllable rectifier to achieve the controllable task. So the field current produces the rotor-magnetic field and controls field current for voltage regulation. And brushed and brushless excitation systems are used. So you can read more about this brushless excitation system. And most of the present machines comprise of brushless solid-state excitation systems requiring low maintenance. Because in these brushless systems, you don't have the maintenance of these brushes or the slip ring or any breakages of the brushes. And then if the fire with the brushes, you have fire hazards, so you can avoid them. So after that, you have the cooling systems. So because of the heating the generator cooling, the heat happens due to the conducting elements on the windings of the rotor as well as the stator windings. The air inside the rotor shaft in the generator itself becomes very with high. It has very high temperature. So you need to have some mechanism to dissipate that heat out from the generator. Otherwise, it could damage the insulation, reduce the performance of the generator, as temperature increase results in the increase in temperatures, increase in resistance of the windings, as well as the reduction in magnetic fluxes on the magnetic laminations. So in order to avoid that, we have cooling systems. And hydrogen cooling of generators is one of the most popular means of means of cooling generators. So we have hydrogen cooling at Lakvijaya. So there are participants from Lakvijaya Nodochole Power Station. So they can maybe explain more on that regarding the hydrogen cooling. So we need due to the resistive losses, which can causes heat dissipation, and air, water, or hydrogen cooled to remove heat from the machine, and the air in the machine can cause windage losses, which reduce machine torque. So we'll see why hydrogen is a effective method. So it's a safe and effective cooling medium when purity is above 75%. That's important because if the purity is low, that means there could be high oxygen present with hydrogen, which is a fire hazard, or like it's really explosive. It is igniting explosively in the presence of oxygen. So it is important to have the purity, high pure hydrogen in the generator for cooling. So with this hydrogen cooling, you can go for smaller generator size and output due to better cooling performance. And hydrogen density is about 7% of the air. Therefore, the windage losses from the moving rotor is getting reduced. So the torque due to that is going to be reduced, torque loss going to be reduced. Mechanical drag increases with lower gas density and depends on the square of the machine velocity, and thermal conductivity hydrogen is 50% higher than air. So it can dissipate heat quickly compared to other generators, and it is relatively inexpensive. So in Nodochole, I believe there is a local hydrogen generation plant. It is a clean, non-corrosive gas, minimizing maintenance needs compared to air-cooled generators. Because hydrogen, because it dissipates the oxygen, displaces the oxygen, and corrosion happens in the presence of oxygen. So it's a better approach for the generator cooling. And the generators have the bearing to basically support the vertical load of the generator and the shaft. So the rotor, runner, and the water thrust. Runner is another word for the turbine. And maintain axial alignment and convert axial force to frictional resistance through an oil film. So main job is to support the generator structure, and then the secondary job is to basically maintain the alignment and convert the axial forces to friction resistance. So with the task of the bearing, you have different types of the thrust bearings: tilting pad, segmental, Kingsbury type, hydrostatic type, and water lubricated type bearings. So you can have a look at them. So let me see. Yeah, so we'll thrust bearing. So you can, with regards to the what are the common issues and failure modes of thrust bearings? Mechanical and the thermal problems are like uneven load distribution, oil film breakdown during transient and low speed operation, shaft misalignment and vibrations, thermal instability and hotspot from poor circulation, and start and stop contact wear, pad or pivot surface damage. So there are, for monitoring parameters, we have the bearing temperature, oil pressure, oil flow, and vibration levels. So the lubrication system is forced oil or oil bath cooling, and then you can look at them. So the maintenance wise, routine checks of temperature, vibration, and oil quality, inspecting pads for wear and uneven loads, maintain alignment and cleanliness of oil systems, and replacing filters and confirm thermocouple accuracy. So these thermocouples inside are installed inside the bearings to monitor the temperature. And if this thermocouple accuracy loses after a long time, the incorrect prediction of uh, the bearing performance will be detected. So then we go into the other control and protection systems of the generator to maintain. So they are used to ensure safe, reliable, and efficient operation of hydrogenerators and detect abnormal conditions early to prevent equipment damage and enable automatic shutdown of or alarm functions when limits are exceeded. The protection category-wise, we can divide them into electrical, mechanical, and operational. Electrical, we have overcurrent differential, earth fault, over under voltage protection, over under frequency protection, over fluxing relays, and different protection electrical categories. Mechanical wise, temperature rise, vibration, bearing pressure, over speed of the generator, shaft alignment. So those kind of elements should be detected as well. They should be monitored and detected for any abnormalities, and take necessary protective actions when they are bypassing the normal or safe operating regions. Then apart from that, we have operational controls with associated with the generator, like automatic speed load control, excitation regulation, and synchronization, with associated with the operation of these generators. Temperature monitoring and protection, it has the with regards to that, the key areas that are being monitored are the stator windings. We have the resistance temperature detectors embedded in the slots to look at the stator winding temperature. Bearing temperatures, as explained, has thermocouples in them, and cooling air or oil temperatures to monitor assess the cooling system performance. We have predictive actions, alarms and warning thresholds, as I said, and automatically increasing cooling flow or load reduction when overheating is detected. Like the generator, the heat dissipations, they it depends on the amount of load that it is being operation, and based on the operational temperature, the current operating temperature, the the operating staff can take action to basically or it can take automatically as well, change the load of the machine so that it can take necessary action to basically reduce the temperatures and come into a safe operating point. And oil temperature and flow interlocks for forced lubrication systems. And the main issues are blocked cooling ducts, loss of coolant flow, and bearing oil contamination, sensor faults. So they can be happening due to rust, different particles, air bubbles appearing in the oil, and sensor damages, as explained. Vibration and shaft auxiliary monitoring, vibration protection. So it's a mechanical device which is rotating at very high speeds. So vibration is a very prone element, and the accelerometers or proximity probes at bearing housing and shaft ends detect this and detect unbalance, misalignment, or mechanical looseness, because the vibrations could be induced because of them. And depending on the amount of vibration and the displacement levels, we can have alarms and trip settings associated with them. So yeah, so we have the I think there's some problem in this slide. Yeah, we'll look at that. With regards to the OM practice of generators, look for vibration, temperature, and insulation resistance, partial discharges. So this is an important characteristic that we do. So the vibration and temperature we looked at. So the insulation resistance is so all the windings in the generator stator and the rotor are insulated with between each of the coils. So we need to make sure that proper insulation is maintained throughout the time, and that insulation resistance should be measured frequently when we have outages. So we can only do that insulation resistance and when we have measure when the generator is on outage, and that needs to be correctly measured and reported. So as the time goes, the insulating material, because it is being stressed at high voltages, because generators typically generate at few kilovolts from 10 kilovolts to about 15 kilovolts. So at that voltage levels, the insulation is getting stressed, and the stressed insulation causes to be can cause failure, like redundant failure. So what, as a safety measure, what we can do is periodically make this measurement, IR measurement, to detect the variation of this insulation resistance. And if it deteriorate beyond a certain level, we have to take necessary action, maybe change the insulation, or do an overhaul of the generator completely. And then partial discharges. So these are the discharges that happen into the air due to the high voltage present. So there is no, in a partial discharge, there is no main arc happening. So it is the air within the high voltage present point, it gets ionized, and electrical discharges are passing into the air, not to the other electrode. So this discharges indicates that there are insulation failure happening and cause losses as well as harmonics in the stator winding output. So these partial discharges can be detected via sound as well as the observing the voltage waveform, and visibly as well. So these things needs to be detected whether partial discharges are occurring in the generator. And if it is so, we need to take necessary repair action, not basically maintenance, repair action, to bring that into proper operating process. And the stator vents and fans to maintain cooling, they should be cleaned regularly, and slip rings and brushes should be inspected, and oil purity and bearing alignment should be maintained. Periodic electrical checks, as we said, in IR, polarization index, and tan delta, all are associated with the insulation of the electrical characteristic. So those measurements should be taken periodically. So now we generated electricity. Now we need to transmit through the by stepping it up and through the transmission system. So first we have a step-up transformer to elevate the voltage that is being generated from the generator. So typical generating voltage from 11 to 15 kV needs to be stepped up to a higher voltage for transmission purposes to reduce losses. So in Sri Lanka, we use 132 kilovolts or 220 kilovolts to do this. And other countries also using to about 800 kilovolts AC transmission networks. Yeah, so this transformer can be implemented in two different ways. One is a single unit with a three-phase structure, three-phase arrangement. So this is a single transformer as a three-phase, a single transformer. The other method is to create a three-phase transformer using three single-phase transformers. So we can have here. So the amount of the cost wise, it is a different decision. The maintenance wise, you have to maintain three transformers. It takes a large space, and the otherwise, if we have a damage, one of the single phase transformers, we can replace it. On the other hand, if we have a damaged three phase transformer, you have to replace the whole transformer. So you have the system. So the key components of the transformers are the main transformer core, transformer windings, bushings, so which are these elements, and the tap changers to adjust the voltage ratio, and the cooling systems, the cooling systems being the air and the lubricating or the oil inside the transformer. So normally the transformer cooling has fans which direct forced air into the cooling fins, like metal fins that cool the transformer oil. And typical faults in transformers are the insulation breakdown within the transformer, overheating, oil degradation, because the transformer is filled with oil. This oil with time, due to reacting with the metal surfaces and the copper and the insulation material, can degrade and degradation will cause the breakdown voltage of the oil to reduce and could damage. And it can also has moisture ingress because the temperature of the transformers go up and down. And with that, water molecules can penetrate through the small gaps on the transformer inside the transformer and cause damages. So we need to do PTD coil tests for breakdown voltage, moisture content, and dissolved gas analysis, because with the operation, air bubbles can appear in the oil, and if these air bubbles are increased, you can have problems with the breakdown voltages. So you need to inspect the cooling fans and the radiators with the transformer. So these kind of fans which are mounted on top of the radiators, you have to see whether there are debris, whether the fans are operational, monitor temperature and load cycles, because that could give a good indication of what is the loading of the transformers, as well as how much the transformer has been used, and take necessary predictive maintenance actions looking at this loading mechanism. And maintain protective relays like Buchholz relay, pressure relief relay, and temperature relay. And most important is to maintain detailed records for trend analysis. See whether you can see any trends of failure at a certain part, and if we see a trend, we can take the necessary action to rectify it. So there's a small explanation I have included in the slides regarding the Buchholz relay, so you can read that. So like that. So it's basically to detect that internal faults and safeguard the transformer during an event of fault. So after the transformer, the power is being directed to the switchyard at the site, the generator plant, and we have the protection systems with the circuit breakers in the switchyard, and it is the main interface between the generating plant and the grid, and it ensures safe transmission of generated power. Equipment, we have the circuit breakers, isolators, current and voltage transformers, and surge arresters, bus bars. O&M activities to basically check contact resistance and mechanical operation, test relays and SCADA systems, inspect grounding systems and lighting protection, because these switchyards are metal structures. We don't have anything higher than this, like around this area. So it has electrical charges present all the time and has a high chance of electric lightning strikes. So you need to properly see them and properly identify them. And the safety regarding the operation and maintenance, so you have to, there are quite frequent operation. In Sri Lanka, it is one of the, I forgot to mention, one of the main aspect of the protection in switchyards is clearing out bird nest, because in these gantry structures, it is pretty common for birds to have their nests. So because of this nest, different animals like snakes can go into there, and even with the monkey incident in February, those kind of debris can cause multiple failures, as you saw. So proper cleaning and maintaining them is highly important. So to carry out this task, since the switchyard is a region which has low hanging high voltage surfaces. So basically this part is grounded, and after these insulators and the surge arrestor components, or these porcelain elements, all the surface at the higher level, we have high voltage elements. So it is pretty closer, still closer to the ground. Therefore, by climbing on these gantries, you can be approaching the minimum safe distance quite frequently. So you need to follow electrical safety procedures when operating in switchyards, proper isolation, earthing, and lockout tagout action to make sure that don't unintentionally create high voltage terminals or surfaces at the switchyard. And you have to maintain minimum approach distance, or MAD, it's approximation. So MAD means like what is the minimum like the minimum distance that you can get from a high voltage equipment. So based on the level of training as well as the level of expertise and the level of technical training, the MAD or the minimal approach distance approved for you might be different. For example, normal engineer who is working in the office might not have the same minimal approach distance as a electrical worker who is a technician who is licensed to work in the switchyard. So some of the technicians might be licensed to work in hotline systems, or that means energized lines itself. So they have very low minimum approach distances. And for the others, depending on the technical clearance, there are minimum maintenance approach distance maintained. So equipment handling like this metal ladders maintaining, so you have different distances that you have to maintain. And you need to, we can do like without going into we can from remotely, you can do like thermographic inspections to identify hotspots to detect any abnormal conditions like done here. And they need to ensure working in these switch charts with IEC or IEEE safety compliance standards. So I have this slide where we have the lockout and tagout process. So you need to review them correctly. So this is just a cartoon indication, but it indicates quite accurately what is the lockout tagout process is. So you have to inform, or get the authorization, shut down the power, deactivate, and lock out so that no one unintentionally operates and depletes. So you have to make sure that all residual energy has been drained from the equipment through proper earthing, and you have to verify during testing that everything is operational, and then restore by the circuit after taking out the lockout tagout system. So apart from this, you have other auxiliary systems for cooling water systems, drainage and dewatering, decompressed air systems, fire protection, communication and control systems like SCADA, alarms and remote monitoring. So in this lecture, this is the conclusion. So this is a brief overview of the hydropower generation scheme. So what I propose is that if we are to go with the so I will get the final conclusion, like what is the actual content that we want to cover, whether is it this one or the new one in the fields which is published. So if it is the fields one, what I will do is I will upload videos like recorded lectures, which will first give an overview of all these generation mechanisms. So we did one for the hydro today. So similarly for the solar and the thermal power, we will do an introductory session first. What is this generation mechanism and what are the key parts that we want to look at? And after that, we will go to this part where which is a combination part for all these generation mechanism systems. Then we can see basically case studies for each of these items individually for each of these power units, power generation system. Otherwise, I don't think we following just the normal in a more generalized sense. It won't give much sense as well into our topic. So I will hope to proceed like that. So any comments or discussions regarding this? So if not, I suggest we'll end for today. And the next one, based on the input, I will upload the recorded lecture, and then we will notify on the next lecture, next discussion. It won't be a lecture. So you can point out the different topics different sections that you want to discuss. And depending as the participants are also they are more, they have the practical knowledge on this, we can have a discussion. So that will be beneficial rather than just doing a lecture on this material. So we can have a discussion like that. So if there are no other questions, we'll end for today. Yeah, so we'll leave the meeting.